Now we're ready to start our discussion of field extensions in earnest. So let's sort of summarize what we're trying to do here. So let's say you have a field and a polynomial equation you would like to solve. Maybe we write that polynomial equation in the form p of x equals 0, right? Just collecting everything to one side. But f doesn't have any solutions. To p. And maybe you know this, for example, because maybe it's something that you just like, you've tried them all, for example, and you just know there are no solutions. In that case, then we have a goal. Find an extension k of f, which does have solutions. And the way that we're going to go about doing this is very reminiscent of group theory and also surprisingly easy. So what we do is first, in order to talk about P as an algebraic object, right? Not just the numbers comprising the coefficients, but the object itself, we form the object f of x, or sorry, f adjoin x. That's what the square braces mean. This is all polynomials with f coefficients. And so, for example, when f is like q or something, these are your rational polynomials. When it's r, it's your real polynomials, and so on. And we saw in group theory, when we were talking about quotients, that when you set a subgroup equal, when you mod out by a subgroup, you're essentially saying all the elements in that subgroup are killed, or they're treated as the identity. So what I want to do is I want to treat p of x as 0, and then see if, like, what that does, right? Like, I'm trying to solve p of x equals 0, so I should set p of x equal to 0. So in other words, what I'm suggesting we do is look at f of x mod p of x. Or in other words, we do modular arithmetic, if you will, or maybe modular algebra, by forcing p of x to be 0. So what does that really mean? In practice, what I'm saying is the objects here are not just normal polynomials, but equivalence classes of polynomials. Where a of x will be said to be equivalent to b of x mod p, when a minus b is equal to a multiple of p, right? In other words, there could be some other polynomial q such that p times q is equal to their difference. This is exactly the same thing as the modular arithmetic thing, right? In modular arithmetic, two numbers are equal when their difference is a multiple of whatever the modulus is. In that case, a multiple means a number multiple. Since we're working with polynomials now, we have a polynomial multiple, but the situation is essentially unchanged. Now, it turns out that this is a field. And so that's going to be the essence of what we'll be proving with the remainder of this video. I mean, we've already been talking for almost 5 minutes. And so we need to check all of this, but that's fine. Let's work through this. So let's start with checking that addition is well defined. So if I have two classes and two representatives, A1 and A2, and B1 and B2, I need to see what happens when I try to add those classes. And so in particular, I have A1, not plus A2, plus B1, and then minus A2 plus B2, right? We're trying to add these things, and I'm trying to take the difference of their representatives. The hope is that this gets me then 0. So if I do this, I can rearrange these guys to get A1 minus A2 plus B1 minus B2. And this is already promising because these things being in the same class means that their difference is a multiple of p. Same thing with these guys. So we expect that if we do a little bit of algebra and we're careful, life will be good. So now, in particular, what I have here is p of x times some, we'll call it q1 of x, plus p of x times some q2 of x, right, from the two different classes. And now I factor this out, and this is q1 of x plus q2 of x. And of course, right, whatever this is still a polynomial. And so therefore, this thing is equivalent to 0, mod p. And so therefore, mod p, I've shown that the difference of these things is 0, which means this is well defined. Okay, now let's look at multiplication. So for multiplication, I need to look at the classes of A1, B1 minus A2, B2. Yeah, that's right. And here I use a standard trick, which probably, if you remember your calculus really carefully, you've seen this trick before. But it's like a random trick that I associate with calculating limits, where we add and subtract the cross terms. And so I'm just thinking really quick, does it matter which one I use? I don't really think so. Let's try this way and see if it makes any difference, although I don't think it does. Although I do think my life will be easier if I do minus and then plus. Maybe it doesn't matter. Here now, if I factor out A1, I have B1 minus B2. And here I have A1 minus A2, B2. Well, after I do this, B1 minus B2, this is some A1 and then a Q1 P minus Q2P. I know that there's X's everywhere, but I'm just not writing that. Oh, wait, hold on. What I said isn't true. Because this is in the same class, that's just a Q1P. Or maybe it should be a Q2P for the B's. Doesn't really matter, right? But since this is in the same class, their difference is a multiple of P. Okay, so this seems to be where we end up. Now, what I notice is this has a P and this has a P. So doing a little bit of collecting of like terms, I get A1 Q2 plus B2 Q1 P. And therefore, that is equivalent to 0 mod P. And that's what I wanted to see, right? That this is well defined, means that their difference is a multiple of P. Okay, so we're now ready to look at the field axioms. And in the usual way, all of them are boring except multiplicative inverses. Right? Associativity is clear of addition and multiplication. Commutativity of addition and multiplication is clear. We know what the identity is. It's 0. We know, or sorry, the additive identity is 0. The multiplicative identity is the class of 1. All of this is very straightforward stuff, right? Like there's some juggling of p's if you really want to be pedantic, but like we know how polynomials work. So that stuff is fine. The hard part is, what is the multiplicative inverse? Right? If I'm only dealing with polynomials, not rational functions, then I don't necessarily know what it means to divide because, well, you can't really divide by polynomials unless you're leaving the world of polynomials. And so this will be the main thing to prove. So here's how we construct this. Let's say you have some non-zero element, a of x. Since a of x is not 0, it's not a multiple of p. That's really what I mean by this. And crucially here, this calculation will fail unless P is what we call irreducible. Irreducible means cannot factor it with these F coefficients. This is crucial because we saw in the previous video that if you can be factored, well, then when I set it equal to 0, the two factors will become 0 divisors, right? If P is Q equal to QR, then the classes of Q and R become 0 divisors. We saw that that's bad. It breaks inverses. So we need to stop that from happening by assuming that you can't factor this. Okay? So therefore, we're going to assume that P is sort of like the analogy of a prime number. In that case, its only divisors will be constants and, well, I guess multiples of itself can be thought of as a kind of divisor because you're working in a field. You could get a fraction as the quotient. That's fine. But the point is, because P cannot be factored, A of X and P of X have the property that their greatest common factor is a constant, which one may as well take to be 1, right? If it was some other constant, it wouldn't matter. The magic is that we can do long division with polynomials. And we have a division algorithm for polynomials to get remainders. More precisely, there is the so-called Bezout identity. Oops, why did that not write? The Bezout identity, which says when you're in this situation, you can find polynomials U and V so that this is equal to 1. This will work in f of x, or sorry, in f of x. In f adjoin x, you can find these polynomials U and V. Now, in our situation, we're working with equivalence classes. When I take the equivalence class of all of this, since we just discussed how all of these things break up and everything is well defined, we get here. But now, when we're talking about equivalence classes, the class of P is equivalent to 0. And so actually what happens is this stuff over here cancels. And so what we see is that the polynomial that was furnished to us by the Bezout identity plays the role of the multiplicative inverse. All right. And so we found a class, right? And what I want you to notice about this is that this is basically just the same proof that I gave for Z mod PZ. The only difference is the extra step here of including the Bezout identity. But otherwise, this is the same story. And so this brings us to a general theme. Try to mimic with polynomials the same kind of thing you do with numbers. And I try to teach this to my students, actually. This is a little bit of an aside, but like for many purposes, it's easier to do things with polynomials than numbers. So in fact, even the reverse is true. Sometimes you want to try to mimic what you do with polynomials to understand how to better do things with numbers. So I'll give you my favorite example of this. It's not really related to fields, but it shows the point I'm trying to make really nicely. In general, It's more annoying to do a big complicated multiplication like this because of carrying, right? You have 12 and 16. Ugh, gross. Now I have to get it, 6 and then 2 is 8. It'd be really embarrassing if this was wrong. I'm going to pull out a calculator and check that it's right because that'd be bad. No, it's wrong. 7 times 6. Why did I write 6 there? How could that be? I'm stupid. Yeah, it's still wrong though. What's going on here? How did I mess this up? 12, 16, because I put a 2. Why is this 2? 7 times 3 is 21. Yikes. Man, that's really embarrassing. But in any case, how about this? And you notice, right? There's no carrying. It all just gets bunched together. And then you get 42 and 33x and 6x squared. And what you'll notice is if you did carrying, now when you set x equals 10, the 4 goes over here and that becomes your 7. This 3 goes over here and that becomes your 9. So like it's actually easier to do this without carrying and then do all the carrying at the end. But I bet no one ever taught you that, huh? This is part of the black magic of studying fields, right? Is that you learn that much of what you want to do with numbers is easier to do with polynomials. All right, let's continue focusing on the task at hand. I have now constructed the desired field extension, although I should probably point out that after I've done this, I've set p of x equal to 0 in here. So let's take stock of where we are. We constructed a larger field. Then f, namely fx mod p. And now we have a question, which is, did this solve the problem? Does fx mod p have solutions to p? Well, in some sense, the answer is of course, because p itself, the class of p, is a solution. But like, what's going on with the numbers, right? Like, or rather, what should I say? In this class, like, how do I explain what the solutions actually look like? And the best way to see this is to look at an example. So let's go back to our previous example with q of x mod x squared minus 2. The elements of this thing can be thought of in two different ways. You can think of them as linear polynomials, ax plus b, where a and b are rational, subject to the condition that x squared minus 2 is treated as 0. In that case, I'm thinking of this as a field element now, right? X is now a field element. However, since x squared minus 2 is being treated as 0, in other words, x is something that satisfies x squared minus 2 equals 0 in this field. So in other words, x is equal to plus or minus the square root of 2. So this field extension concocts an element, namely this x thing, that plays the role of square root of 2, or its negative. So functionally, this has created a new number. So if I do this with higher degree polynomials, like instead qx mod x cubed minus 2, then I get two classes of new numbers. I get all things of the form a plus bx plus cx squared, where a, b, and c are all rational numbers, because if I go up to x cubed is equivalent to 2 modulo that polynomial. And so I have new numbers x and x squared playing the role of the cube root of 2 and the cube root of 4, or the cube root of 2 squared, or the cube root, the cube root. Right, that's the same thing by elementary algebra. And so what we're seeing is these powers of x produce the new field elements. Now, it's a little bit of a question, given a more complicated polynomial extension, how I can actually cook up the inverses. But this nevertheless gives us the big theorem of this section. And so I should write this theorem down and just make it a precise statement, and then we will be satisfied. So this I'll take from Pinter. So let F be a field, and A of x, this is his notation now, a non-constant polynomial in F of x. Then there exists a field extension. He calls it E. That's a little bit annoying. I was calling it K. It doesn't matter. Field extension E of F containing roots of A. Okay, there's one last remark that I need to make about this, which is that in this statement, he does not assume that A of x is irreducible, that it's not factorizable. So if you want to extend this to the factorizable case, right, the situation where it's reducible, then what you have to do is find the so-called minimal polynomial of whatever the root is you're interested in. So in other words, if C has A of C equals 0, and A is reducible, perhaps A of x splits into P of x, Q of x, right? Since this is a root and it takes value in a field, the only way to multiply two numbers and get 0 is if one of them is already 0. And so what this means is C solves one of P or C. It could solve both of them, but no matter what, you can just basically keep going, keep dividing, keep factoring until you find all the components which are irreducible, and you only need one of them then. Just take one and repeat this construction. That will give you a larger field containing a root. All right, very cool. This is the end of the discussion in chapter 27. It all fit nicely into one video once we did the hard work of, well, explaining all of this. And I guess it is a pretty long video, so maybe it didn't fit nicely. But in any case, after this, we are back to our regularly scheduled programming of a couple of short videos per chapter, and life will be good.